faithfully delivering value, interpreting great books from around the world. Hi, this is Sally Talking Books. Today we're interpreting the book The Elegant Universe for you. Hmm. Do you remember the 2014 sci-fi blockbuster Interstellar? The film tells the story of the protagonist Cooper embarking on a space adventure to save humanity. Hmm. Cooper risked his life, enduring the pain of parting with loved ones, and boarded a spaceship to find a planet suitable for human survival. This film not only gained recognition from audiences, but also from physicists. Stephen Hawking praised it, saying the film incorporates many theories of modern physics, like relativity, black holes, singularities, wormholes, higher dimensional space, and so on. These theories are perfectly blended with the storyline, making it both thrilling and somewhat believable. But many people might not grasp it fully after just one viewing, because concepts like black hole, singularities, and higher dimensional space are very profound for the average viewer. Moreover, these concepts are all tied to a mysterious theory, which is the cutting edge of modern physics, string theory. The emergence of string theory has led to tremendous advances in modern physics. Why is string theory so magical? Listen to the book The Elegant Universe, and you might find the answer. The English original of this book was published in 1999, ranked fourth on the New York Times bestseller list that year, and won the 2000 Aventis Prize for Science Books. This book has been hailed by media like the New York Times, Science, and Scientific American as one of the best popular science books on string theory. A documentary adapted from this book, The Elegant Universe, won the Peabody Award for Excellence in Broadcasting. The author, Brian Greene, is a world-leading physicist with a PhD in physics from Oxford University and a professor of mathematics and physics at Columbia University. He has always worked at the forefront of string theory research and has made significant contributions to studying spatial forms in the theory. And Greene says, he wrote The Elegant Universe to share the astonishing discoveries at the forefront of physics with readers. This book is about 360,000 words and will interpret it in three parts. Part 1, why do we need string theory? Part 2, what exactly does string theory say? Part 3, what are the implications of string theory? Next, we'll tell you about Part 1, why do we need string theory? To talk about string theory, you first got to understand two things. One is general relativity, and the other is quantum mechanics. Let's start with general relativity. General relativity says that massive objects cause space to bend, and curved space changes how things move. For example, a huge object like the sun bends space, so it alters Earth's motion. To help you get it, let's do a thought experiment. Imagine placing a bowling ball on a flat rubber sheet. The sheet will deform. Then we gently roll a small marble onto the sheet. The marble will roll along a curved path. Doesn't this scene of the marble rolling down the dented rubber sheet look like the marble's being pulled by the bowling ball's gravity? Okay, now think of the rubber sheet as space itself, the marble as Earth, and the bowling ball as the sun. Einstein proved that the sun's existence causes space itself to curve. The effect of space bending on nearby objects is the same as the gravitational force pulling them toward the sun. In other words, gravity happens cause massive objects warp the space around them, and that curved space creates the pull. Space bending is gravity. That's the core idea of Einstein's gravity, or general relativity. So what is quantum mechanics? Quantum mechanics deals with tiny particles, and it's even more elusive than relativity. The uncertainty principle in quantum mechanics says you can't pin down a particle's position and speed, or energy and time, all at once. Or, the smaller the scale or shorter the time, the crazier the particle gets. Picture an electron trapped in a box that can shrink. You slowly squeeze the box to make it smaller. Then you'll see the electron acting all claustrophobic, bouncing around faster and wilder, totally unpredictable. Actually, any particle crammed into a tiny space goes bonkers, like a foamy mess that keeps bubbling and changing. So basically, on a tiny scale, the universe is a chaotic, crazy place. Physicists call this quantum foam or quantum fluctuations. Up to here, we've covered the two big pillars of modern physics: general relativity and quantum mechanics. So, what do they have to do with the theme of this book, string theory? General relativity and quantum mechanics have been verified by countless experiments and facts. They're both correct. One handles the macroscopic world, the other explains microscopic particles. The macroscopic world explains microscopic particles. However, in certain special scenarios, like at the center of a black hole or during the Big Bang moment, cosmic matter has huge mass but tiny scale. At these times, we need both general relativity and quantum mechanics, yet conflicts arise. When you combine the equations of both theories, well-posed physics problems yield no meaningful answers. In the macroscopic world, spacetime is smooth like that rubber sheet, continuous and stable. Only then can we effectively apply general relativity. But in the microscopic quantum world, everything is discrete, discontinuous, and unstable. To resolve the conflict and harmonize general relativity with quantum mechanics, physicists racked their brains and made countless efforts. They tried all sorts of methods, either modifying general relativity or tweaking quantum mechanics. Although each effort was bold and innovative, it still ended in failure. After failure upon failure, string theory finally made its entrance. Next, we'll tell you about part 2. What exactly does string theory say? Classical physics holds that matter is made up of point-like particles. Layer by layer, paced for complexity, matter is composed of atoms, atoms of nuclei and electrons, nuclei of protons and neutrons of quarks. Protons and electrons seem like point particles with no internal structure, so they're called fundamental particles. Physicists developed a series of theories that basically explain why there are so many fundamental particles and the forces between them. String theory proposes that if you zoom in on fundamental particles, you'd find they're made of tiny loops. Each little loop is like an infinitely thin rubber band, constantly vibrating. Physicists gave these vibrating bands a vivid name: strings. Different vibration modes of the strings form different fundamental particles. We can think of the strings in string theory like those on a violin or guitar. By different fingerings and playing strengths, the same string can vibrate differently, producing different sounds. Strings in string theory are like this. Although all strings are the same, they have different vibration modes, so they can produce different fundamental particles. An electron is a string vibrating in one mode, while a quark is a string vibrating in another mode. If the amplitude of the string is large, the particle it produces carries high energy. In other words, all matter in the universe is actually composed of strings. The colorful world we see is in fact constantly vibrating. String theory is an evolving theory. It's constantly being refined and innovated, with new ideas emerging all the time. And some of these ideas are quite shocking. Next, we'll present 2 new viewpoints of string theory, and you'll get a feel for it. The first viewpoint is that string theory posits the spatial structure of the universe is 11-dimensional. Physicists, through mathematical deduction, have found that the universe in string theory should have 10 spatial dimensions, plus 1 time dimension, making a total of 11 dimensions. My 11 dimensions. Physicists derived this from the basic conception of string theory through scientific calculations. Only an 11-dimensional space can accommodate all physics laws without contradictions. Of the 10 spatial dimensions, 3 are expanded, that's the 3-dimensional world we experience, while the other 7 are curled up. Because these curled up dimensions are so small, even the most precise instruments can't detect them, so we don't perceive their existence. And to help understand curled up dimensions, let's use an analogy. Imagine observing a long, suspended water pipe in a garden. Up close, the pipe has thickness. If an ant is crawling on the pipe, it can crawl along the length of the pipe or circle around it. So that circling direction is also a dimension. From the ant's perspective, the space is two-dimensional. But if we step back and observe the pipe from afar, it looks like a line with no bigness, making it seem one-dimensional. Similarly, the universe is like this pipe. Some dimensions are expanded, others curled up. The second viewpoint is that string theory sees black holes and fundamental particles as essentially the same. What is a black hole? Black holes typically form from stars with masses tens or hundreds of times greater than the sun. When such a star evolves to its end stage, becoming a neutron star, gravity continues to compress it, causing it to collapse. According to German astronomer Schwarzschild's research, when a neutron star collapses to a state where mass concentrates in a sufficiently small spherical region and mass divided by radius exceeds a critical value, spacetime undergoes extreme curvature, forming a black hole. A massive gravitational field surrounds a black hole. Anything approaching it gets sucked in. Not even light can escape from within a black hole. For a star with solar mass to form a black hole, its critical radius is about 3 kilometers. Hearing this, you might wonder, black holes are such massive celestial bodies, while fundamental particles are countless times smaller than dust. How could they be the same? Don't worry, let me explain it step by step. Physicists previously discovered that any two black holes with identical mass, charge, and spin are completely identical, just like fundamental particles, where these are defining attributes. Here, let's clarify particle charge. It's a particle's response to interactions with other particles. In fact, what we call electric charge is a type of particle charge. It's a particle's response to electromagnetic force. Due to this similarity between black holes and fundamental particles, some physicists proposed a bold hypothesis. Black holes might be giant fundamental particles, but their differences seem so extreme, like fire and water, utterly incompatible. It wasn't until string theory emerged that this concept was validated. Starting from string theory, physicists performed incredibly complex calculations and found that under certain conditions, massive black holes can transform into massless particles. In string theory, that's simply a string vibrating in a specific way. So string theory directly links black holes and fundamental particles. They're like water and ice, the same substance in different forms. How about that? After these two viewpoints and explanations, you might still feel it's a bit too fantastical. Although these ideas seem peculiar and hard to grasp, they weren't conjured by physicists. They emerged from rigorous calculations and theoretical derivations. You might still ask, what's the practical use of string theory? Well, that's exactly what we'll cover in part 3. What's the use of string theory? Let's talk about it from 3 aspects. First, string theory resolves the conflict between quantum mechanics and general relativity, bringing us closer to the ultimate theory of physics. Earlier, we mentioned that in general relativity, the universe is like a giant membrane. Objects can bend it, and space appears smooth. But in quantum mechanics, space at the microscopic scale is discontinuous, so they conflict at that level. String theory suggests that the conflict between quantum mechanics and general relativity only appears at scales smaller than the Planck length. The Planck length is 10 to the minus 33rd centimeters, which is an incredibly small scale. And how small is that? Suppose we enlarge an atom to 10,000 times the Earth-Sun distance, and then magnify the Planck length by the same proportion. How big would it become? It's still smaller than a speck of dust. In string theory, space isn't infinitely divisible. Fundamental particles have a size limit. How small can they get? as small as the average length of a string, which is the Planck length. Thus, space fluctuations below the Planck length are imagined, not real. So, the so called conflict between quantum mechanics and general relativity doesn't exist anymore. For example, if you touch a finely polished marble surface with your hand, it feels perfectly smooth. But if you look at it under a magnifying glass or microscope, you'll find that the marble surface is uneven, with many tiny grains and pits. It's just that they're too small. Our hands can't feel them. Similarly, because strings have a spatial size, their sensitivity to small scales has a limit. Just like our fingers, strings can't perceive changes below the Planck scale. In this analogy, the tiny grains and pits on the marble surface are beyond the perception of the hand. For the hand, they're meaningless. Physicists worldwide have long dreamed of creating a theory that can explain all natural phenomena. One fundamental requirement is unifying the four fundamental forces of the universe, including gravity, electromagnetic force, strong force, and weak force. This theory is the unified field theory, also known as the ultimate theory of physics. Quantum mechanics unifies the other three forces except gravity, but fails to incorporate gravity. By resolving the conflict between general relativity and quantum mechanics, string theory actually incorporates gravity into its framework, thus taking a crucial step toward the unified field theory. Though string theory still has imperfections, physicists increasingly believe it's on the right track. Second, string theory has helped us locate the starting point of the Big Bang. While the Big Bang theory is now accepted by most physicists, they still can't describe what the starting point was actually like. According to general relativity, if we rewind time, the closer we get to the Big Bang's start, the denser and hotter the universe becomes. At the exact zero moment, density and temperature reach infinity, a result that's unacceptable. Or rather, the theoretical model producing this outcome is flawed. But string theory proposes that at the Big Bang's start, the universe wasn't infinitely small. It had Planck scale dimensions in all directions. Imagine it as a tiny fireball with a diameter of only Planck scale. At that time, all dimensions of the universe were curled up. As the Big Bang began, three spatial dimensions expanded while the others remained at Planck scale. These three unfolded dimensions evolved and inflated, forming our present universe. Third, string theory makes traversing spacetime possible. Hawking proposed parallel universes exist, and some physicists believe black holes are seeds of new universes that can erupt from them. Parallel universes are like soap bubbles floating in air. Our universe is just one ordinary bubble among countless others, usually separated, but wormholes connecting these parallel universes might exist. Through wormholes, humans could travel between different bubbles. This isn't sci-fi, it's become serious research for physicists. So, what exactly is a wormhole? Earlier, we mentioned that in black holes, the gravitational field is infinite. Anything approaching gets absorbed and destroyed. But some scientists suggest that black holes don't collapse to a point, but are compressed into a ring. When an object falls onto this ring from the side, it gets absorbed by the intense gravitational pull. However, at the center of the ring, gravity isn't infinite. If an object passes through it, it could survive. So this black hole becomes a gateway to another universe, a wormhole. And time flows at different rates at each end of the wormhole. Thus, wormholes could take us back to the past or forward to the future, like in sci-fi stories. Space travel and futuristic could become possible. Human survival in space would gain much more freedom. String theory is truly incredible, but it's still evolving and imperfect. Physicists are constantly improving it. Why do we say that? For one, strings are incredibly tiny, averaging around Planck length, and we have no experimental methods to observe them clearly. Even with our most advanced instruments, they still look like points. On the other hand, the mathematical tools for studying string theory aren't fully established. Um, When Einstein built general relativity, the powerful math tool of Riemannian geometry was already available, developed 60 years prior. But string theorists haven't had such luck. String theory is too deep, and creating a perfect, all encompassing physics theory is tough. For the ultimate theory, humans still need to put in immense effort. Okay, we've covered the main content of the elegant universe. Now, let's quickly recap the three parts we discussed today. First, we talked about the background of string theory. The two pillars of physics, general relativity and quantum mechanics, have been validated by numerous experiments and observations. But in extreme cases, like at a black hole's center or during the Big Bang, they conflict. So a new theory is needed to solve this. This new theory is string theory. Second, we covered the fundamental concepts and novel ideas of string theory. String theory proposes that fundamental particles are made of tiny vibrating strings with very small scales. Typically, at Planck scale, string theory research has yielded revolutionary ideas, such as the universe having an 11-dimensional structure and black holes and particles being fundamentally identical. Finally, we discussed string theory's impact on physics. It resolves the conflict between general relativity and quantum mechanics, establishes a framework for unified field theory, refines the Big Bang theory, and makes time travel possible. In short, string theory paints a whole new cosmic picture for us. From Earth's mountains, rivers, forests, and oceans, to the stars in the vast cosmos, from tiny dust particles to massive black holes, everything is a marvelous melody played by vibrating strings. Though still imperfect, string theory's achievements amaze us, giving humanity confidence and hope in exploring the universe's ultimate mysteries. All right, that concludes our interpretation of the elegant universe. The reading notes are below the audio. See you tomorrow.